So just to remind you how electron guns work, you take high voltage, heat up some electrons with a filament, and then persuade the electrons to move at high speed by putting a few thousand volts of electrical potential between them, and you should get a nice stream of electrons moving through. So what we're going to do is switch on this magnetic field. At the moment the electrons are running straight through, as you can see that. By the time I put in these coils, that's going to make a magnetic field run perpendicular to the path of the electrons, because a coil will give you magnetic field running up and down through the coils. So 2 coils is going to give you a strong magnetic field towards where you're looking at. Because the force is perpendicular to both the velocity and the field, what happens to the force? It changes as well, doesn't it? It's still the same number of newtons of force, because it's still in the same field B. Because the force is just, it's not the size of the force that changes. What's changing?
The direction.
The direction. The direction is always 90 degrees to the movement. Yeah. It's a circular force. It's a circular motion. Right? It's a circle. If we kept it going long enough, it would wrap itself around in a circle. Why?
Because the force is always at 90 degrees.
Yeah. And if a force is always at 90 degrees to something which is moving, it provides a central force. It provides a centripetal force. So this magnetic force is actually providing a central force to keep it in a circle. So it would actually wrap itself round and round in a circle there. And so if we bump the magnetic field up a bit, you would see the force, the radius getting smaller and smaller, because it's trying to wrap itself around in a tighter and tighter circle, because the central force is getting bigger and bigger. Now unfortunately you need Helmholtz coils that are about this big, and a dirty great big glass flask costing about thousands of pounds, which you might see in a university, but unfortunately we don't have them. And then you can see the electron just go, well, you don't see the electrons moving because they're going too fast, but you'd see the circular path of where the electrons get trapped in this circle. And that's it, they just keep going round and round in circles. A bit like some of you doing calculations sometimes. So, that's the theory for it. What we now need to do is think what would be the radius, calculate what the radius would be if you know the speed of the electron coming in and you know the magnitude of the magnetic field.
So
What happens to an electron if it does go into an electric field? I'm going to assume here that the force, the field that we've got is going into the board. So in that case you would draw the field as being circles with crosses going in. So we've got a magnetic field going in like that. So we're drawing the field lines with fingers like that. An electron's going to come in here. So that's a negatively charged electron. It's going to hit the magnetic field, and as soon as it's in the magnetic field, the force that's on it is always perpendicular to its motion, so it will go round in a spiral, assuming that we can avoid the magnetic field at that part there. Now the force that's on it, F, is equal to Q VB, where that's always perpendicular to the velocity. If we know what the mass of the electron is, m, you should be able to work out what the radius of the movement is as it goes round, like that. What's the equation for central force that you should know from mechanics? Chris? I thought you were going to. Okay, so. Sorry, Alistair? Equation for central force? Yeah, mv squared over r. So the central force is mv squared over r. So if you're trying to find the actual radius, if you know what the charge is q, if we know what the magnetic field is b, and we know what the mass is, we can equate these two forces because the magnetic force provides the central force. So you've got qvb equals mv squared over r. So cross-multiplying the radius, that v squared will cancel one of the v's on that side, so you've got r is equal to mv over qb. So the radius is bigger if the velocity of the electron is higher, and the radius is bigger if there's more mass, because both of those make it more difficult to keep the electron in a particular orbit. One, it's going faster, and secondly, it's a bigger mass, so you'd need more force. If the charge is a bigger charge, you'll end up with a smaller radius. What would be the thinking of that? Why will you end up with a smaller radius if you've got a bigger charge? Don't?
The force will be bigger?
Yeah, the magnetic force, QVB, is bigger, so it'll hold it in a tighter radius. And similarly with B, the bigger the magnetic field, the tighter the radius. So if you're a big collector of equations, you can learn that one. Given that it's based on two equations that you should know, I would generally just derive it or use it in the question as you need it. And that's the direction for a negatively charged electron. If you had a positively charged alpha particle or a positron, in that case it would go the other direction round for that magnetic field going into the page. If the magnetic field was coming out the way with an electron, again it would be the other direction.